Today we will solve a problem that involves rotational dynamics and rolling and slipping. So it's a problem in rotational dynamics, and it's a problem that involves rolling and slipping. All right, here's the problem. Suppose there's a symmetrical body like a disk or a cylinder that is rotating with omega 0, and it is above a horizontal plane, and the parameters of the disk are: it has mass m, radius r, and moment of inertia 1/2 mr square. It has no translational motion, it's just rotating. We lower it slowly onto the surface and let go. What happens? What happens is that, let me just erase this part, make it lower. It is rotating with omega 0. It touches this point. Let's call it O. And it is slipping over the surface. But as it slides over this surface applies a force, friction force, on the disk. So there's a friction force on the disk, and it starts moving to the right. And as you can imagine, since F is against the direction of, against this rotation motion, it will slow down this rotation as it moves to the right. And there will come a point where it reaches a velocity Vf such that there is no more rolling and slipping, it's only rolling without sliding. So the kinematical constraint for that is omega f r. So this distance is d. All right, so the given in the problem are the parameters of the disk and omega 0 and mu, and of course we have gravity here, and find bunch of things. Find, for example, the final angular speed of this object, linear velocity of the object, and so if time equals 0 here, time equals t here, when does this happen, when do we reach there, and what is this distance? So until it reaches this, central mass reaches this distance, there is this rolling and sliding over this surface. Okay? And what about the work done by the friction force? Because friction force, it's not, this thing is not going up and down, so gravity doesn't do any work. So the only force that does work is friction. And friction is pushing this object to the right, but it's also applying a torque. So it's making rotational, translational work and work in the rotational motion. And what is the final energy? E translational, E rotational, final. And we can also look at E of x. So this is x. How does the total energy vary with x? So let's start. The free body, I only write the horizontal forces is F. So F is mu mg, that's the coefficient of friction, and this is equal to ma. So the linear acceleration is just mu g, and F acts from here to here, namely from time equals 0 to time equals t. So F dt is j. It provides an impulse, and this impulse changes the linear momentum and the angular momentum. So j is equal to mvf minus mv0, but initial velocity is 0, so it is simply mvf, and putting the kinematical constraint in, it is m omega f r. Okay, that's the linear impulse. How about the angular impulse? So let's make a sense of rotations. Initially it is rotating this way, so let's take this rotation as the plus. The torque applied by the friction is torque, the F equals ma equivalent for the rotation is tau equals I alpha, and tau is minus Fr, because it is in the opposite direction to this sense. Okay, so this one is minus Fr is equal to I alpha, and well, we can find alpha from here. Minus mu mg r is equal to 1/2 mr square alpha, and m's gone, r is gone, minus 2 mu g over r is equal to alpha. That's the angular acceleration. Since these are positive, angular acceleration is deceleration. So angular speed is decreasing as we expect. And if you time integrate this equation, that is minus jr. This is the angular impulse due to the friction, is I omega f minus omega 0. This is the final angular momentum, and this is the initial angular momentum. And we can solve this equation because here between this equation and that equation, we can eliminate j. J is m omega f r. So it is minus m omega f r times r square. That's equal to I omega f minus omega 0. There is only one unknown here. Omega f is equal to, we take this one to here, that one to the right, I over I plus mr square omega 0. And if we put the value of the moment of inertia of the cylinder, 1/2 mr square divided by 3/2, so it is omega 0 over 3. And Vf is omega f r, that is omega 0 r over 3. So perhaps I will erase this. Explains the geometry of the problem. So I will write here the our results. A is mu g, so that we don't have to redo it every time we need it. Blackboard is small. And alpha is minus 2 mu g over r, and Wf is W0 over 3. Okay, I'm erasing this part. So we solve these. What about when does this start rolling without slipping? When does it come to here? So omega of t is omega 0 plus alpha t. That's equal to omega 0. Alpha we found is that's 2 mu g over r. So it is minus 2 mu g over r and t. And we know that omega f t, namely omega f is equal to omega at t, and this is omega 0 over 3. So we write omega 0 over 3, that's equal to omega 0 minus 2 mu g over r and t. So we take it there. 2 mu g over r is equal to 2 over 3 omega 0. 2's cancel. There's a t here. T is omega 0 r over mu g and 1 over 3. So let me write here. T equals 1 over 3 omega 0 r over mu g. Dimensions checked. This is L over T. This is L over T square, so it's T. All right. How about D? D is 1/2 a T square. Because there was no initial velocity, V0 was 0. V0 was 0. And the starting point we took is 0 along the x-axis, so it's simply 1/2 a t squared. So it is 1/2, a is mu g, and t squared 1 over 9 omega 0 r square over mu g square. So this knocks it out. So it is 1 over 18 omega 0 r square over mu g. Let's check the dimension. Upstairs is L square over T square. This is L over T square, so it is L. The dimension is length, so it's okay. So let me write it here. D is equal to 1 over 18 omega 0 r square over mu g. Now, let me multiply both sides by mu g, and in fact by m mu g. So m mu g times d, that's equal to 1 over 18 omega 0 r square over mu g. And I multiply by m. Just a minute. I'm multiplying by mu g and m. So mu g is gone. That's equal to 1 over 18 m omega 0 square r square. This is 1 over 2 mr square times omega 0 square over 9. I divide by 2 and I multiply by 2. So this is the moment of inertia. So this is just the energy. So it is 2 over 9 E0 rotation. So this thing initially had energy E0 rotation. It was all rotational, 1/2 I omega 0 square. So what happened? This is the work done by the friction force. This is just Fd. So the friction force does positive work, and W friction translation divided by E0 rotation, that's 2 over 9. So the friction force adds 2/9 of the initial energy, pumps it to the translational motion. So let me write W friction translational over E0 rotation. Initial energy is 2 over 9. I'm racing. But friction does not only do work that contributes to translational motion, but it also does work that contributes to the rotational motion. So let's find that out. The kinetic energy rotation is equal to 1/2 I omega f square minus 1/2 I omega 0 square. Omega f is omega 0 over 3. So it is 1 over 9 minus 1 E0 rotation. So it is minus 8 over 9 E0 rotation, or this is, well, who does this work? That's the friction. So the work done by the friction for the rotational mode divided by E0 rotation is 8 over 9. So let's write here W rotation friction over E0 rotation is 8 over 9. Therefore, if we write WF translation plus W, this is friction rotation divided by E0 rotation, that is minus 8 over 9 plus 2 over 9. That's minus 6 over 9, or minus 2/3. That is, friction essentially wastes about 67, 2/3 is roughly 67. 67% of the initial energy is wasted, but it is divided into 2. In the rotation it does negative work, and in the translation mode it does positive work. But the sum, of course, is again negative. All right. There is something interesting, an interesting graph that we can draw. I'm erasing this part. I hope it's all clear. Is this. How much did it rotate until from here it comes to here? Okay, the center of mass went a distance d, but O was the point on the axis, let's call it P. Okay, so P rotates, it is moving and sliding. So at the end, P has rotated by an angle theta, or covered a distance r theta. So what is this compared to D? Now it turns out you can do it algebraically, but let's do it graphically. Here is the time axis. This is t. And let me call this omega 0 r. I divide it into 3. Omega f is 1/3 omega 0 r. And when time t comes, this is v. Remember, v is at. A is mu gt. And at this point, it reaches Vf, because this is omega f r, which is simply Vf. So this is the translational speed, V translational. Now the rotational speed, I will call it omega r. And we found omega is omega 0 minus 2 mu g over r, it's there, r times t. And if I multiply by r, that's 2 mu g. So it is made into a linear speed, and this is the rotational speed. So it is decreasing like that. Here they meet, and from then on, there is no longer there is friction, because otherwise the disk would accelerate. It would simply move with a constant speed. Now, if you notice, this area is just d, because d is 1/2, v is this is at, and t. Okay. Remember, we found it before, so I don't need to calculate. But d is simply this area. How about r theta? R theta is the area under this. Okay, so this is the d. Now r theta is the area. I'm erasing this. Under this whole thing. Here I have a triangle, and I have a rectangle. So let me calculate the area here. R theta is, this is 2/3 omega 0 r times t times 1/2, because it's a triangle. 2/3 omega 0 r is the base height, and 1/2. That's the, and this one is omega 0 plus omega 0 r over 3. That's the area of the rectangle here. I am looking at the area under this curve, up to here. Omega 0 r times t. And so equals omega 0 r t parenthesis. That's 1/3 plus 1/3. That's 2/3 omega 0 RT. And how about D? D d is this. Let's calculate it in the same way. D is the base omega 0 r over 3 times t divided by 1/2. So r theta divided by d, omega 0 rt over 3 is cancelled. That's 2 over 1/2. That's equal to 4. So r theta is equal to 4 times d. Namely, even though the center of mass traveled a distance d, the point P in its linear distance went for a distance 4d. Okay, so r theta is 4d. Okay. As a last computation, let us consider E as a function of x from x equals 0 to d. How does the total energy change as our object travels from 0 to d? Therefore, we can write this energy in the translational mode plus energy in the rotational mode. This is the total. The object, the cylinder, gets its translational kinetic energy due to the work done by the friction force. So E translational x is equal to mu mg, that's F, times x. But I want to make it dimensionless, so I divide by d and multiply by d, and I define a variable, dimensionless variable, x over d. So it is mu mgd times eta. And mu mgd is the energy when eta is equal to 1. Eta changes from 0 to 1. But we already calculated it. That's 2 over 9 times initial energy. So E translational, and instead of x, let me use eta divided by E0 rotation. That's the initial energy. That's simply 2 over 9 eta. Now the rotational. E rotational x is equal to 1/2 I omega square, omega t square. Okay, so that's 1/2 I. Omega is omega 0 minus alpha t. Omega 0 minus alpha plus alpha t, and alpha is minus 2 mu g over r t square. Now we have t, but we were calculating in terms of x, so we have to shuffle the. So x equals 1/2 a t square, which is 1/2 mu g t square, and t is 2x over mu g, 2d over mu g times x over d, which is eta t square. So t is root 2d mu g times root eta. So omega of x is equal to omega 0 minus 2 mu g over r root 2 over mu g. Now d. D we find here 1 over 18. 1 over 18. Omega 0 r square. Omega 0 r square over mu g times root eta. So mu g cancels this, r cancels that, omega 0 comes out, and this is 1, this is 9. So it is omega 0 minus 2 over 3 times omega 0 times root eta, which is omega 0, 1 minus 2 over 3 root eta. Now, that is, I will write it as 1/2 I omega 0 square 1 minus 2 over 3 root eta square. So this is simply the initial rotational energy. I don't need these anymore. I'm missing this part also. So E rotational eta divided by E0 rotation divided by that, that's 1 minus 2 over 3 root eta square. Let's square it. 1 minus 4 over 3 root eta plus 4 over 9 eta square. Let's see what is it when eta is equal to 1. Eta is equal to 1 means distance is d, time is t. Okay, so this ratio equals 1 minus 4 over 3 plus 4 over 9. Not eta square, eta. 4 over 9. So it is 9 minus 12 plus 4 divided by 9. (13 minus 12), so it is 1 over 9. So the rotational kinetic energy is 1/9 of the initial rotational energy. So it starts as 1. 8 over 9 of it is eaten by wasted by the friction, and 1 over 9 comes in the rotational energy. Okay, so this goes down to 2 over 9, and this goes to 1 over 9. So at the end, the total energy is 1/3. But let's see how it approaches. So let's add them. E total eta is equal to, so 2 over 9 makes 6 over 9. So 1 minus 4 over 3 root eta plus 6 over 9, which is 2/3 eta. Okay, that's the total energy. Now it's interesting to see how it approaches to eta equals 1. So let's differentiate. This is divided by E0 rotation. So So let's call it ratio what? Some ratio psi, let's say. Okay, so d psi, just to avoid to write, d psi d eta is equal to minus 4 over 3, 1 over 2 root eta plus 2/3, 1, 2. So it is 2/3, 1 minus 1 over root eta. That's the derivative of basically energy with respect to eta. I can erase this part now. What is it saying? Remember, psi is total energy divided by E0, and we are looking at it as a function of eta. Eta is equal to 0, it is here. Eta is equal to 1, it is here. You see, when eta is equal to 0, when at the start of the motion, the change of rotational energy is very fast, almost infinitely fast. And at the end, when it goes to 1, it is 0. So roughly speaking, this is E total over E0. So at the end, this is minus 2 over 3, 1 over 3. So it is 1. This is 1 over 3. This is eta. This is 0. This is 1. So it is going to come down from here to there. But you see, it comes down very fast here. Eta is equal to 0 minus a large number, and is tapering off. And here, okay, that's the way total energy is changing. And at the end, 2/9 of it is in the translational motion, 1/9 of it is in the rotational motion. You add them up, that's 1/3 of the initial energy. It just says that if you go the same distance, delta eta, remember eta is x over d. First you lose a lot of energy, then you go another delta eta, you lose a little less energy, then less energy. Okay, so when you come to here, derivative is 0, you are no longer losing energy. In summary, we took a cylinder that was rotating with omega 0, put on a rough surface, there is friction, it starts accelerating due to the friction. Friction is doing positive work in the translational motion, but it's eating up, wasting its rotational kinetic energy. And finally, the translational velocity and the angular final velocity have this rotation without sliding constraint. And we found not only the final energies, but how does the total energy vary along the distance. Okay, that's it.